Okay, so let me briefly review what we discussed in the last lecture. We were discussing the process of canonical quantization. And we started with the fundamental commutation relation, which is phi of x t, pi of y t. The commutator of phi and pi is I delta x minus y, where this is the Dirac delta function, and we were discussing the example of Klein-Gordon field for which the Lagrangian density is given by L equal to half del mu phi minus half m square phi square. We have seen that the Hamiltonian is integration d cube x half phi dot pi square plus grade phi square plus m square phi square, and we need to find the spectrum for this Hamiltonian. In order to do that, we were considering the plane wave solution to the equations of motion. So, the plane wave solutions are of this form: phi is e to the power minus I k dot x, where k dot x equal to k0 x0 minus k dot x, and k0, which I also denote as omega, is square root of k square plus m square. Then any general solution to the classical equations of motion can be written as a superposition of these plane wave solutions. So, the most general phi is written as integration d cube k over 2 pi cube 2 omega times a of k e to the power minus I k dot x plus a dagger k e to the power I k dot x. Here this 2 omega is for convenience, and when we quantize, these phi and pi's are operators, and hence the coefficients here a k and a dagger k are operators. We wanted to find the corresponding commutation relations for these operators, which are a k and a dagger k. To do that, we invert this relation and we express the operators a k in terms of phi and pi. So, this is what we have done in the last lecture, and the result is a k is integration d cube x e to the power I k dot x I pi of x plus omega phi of x a dagger k is d cube x e to the power minus I k dot x minus I pi of x plus omega phi of x. What we will now do is, we will find what is the commutation relation a k, a dagger k prime. All right. So, this commutation relation will simply be integration. We have two integrations. In the first, I will use x as the integration variable, and in the second expression, I will use x prime as the integration variable. So, d cube x prime, and from this I will get e to the power I k dot x, here minus I k prime dot x prime, because the argument of a dagger is k prime and the integration variable for a dagger I am using as x prime, and then the commutator of these two quantities. While evaluating the commutator, you must remember that pi of x commutes with pi of x prime, and similarly phi of x commutes with phi of x prime. So, keeping this in mind, the commutator of these two terms will become here I omega and commutator of phi of x prime. So, I omega pi of x t phi x prime t, because we are considering equal time commutation relations. And similarly, here I will get the commutator of phi and x. So, minus I omega phi of x t and pi of x prime t. Now, we will use the fundamental commutation relation, which is this commutator here is I delta x minus x prime. Similarly, here the commutator is minus I delta x minus x prime. So, when I use that, what I get is integration d cube x prime e to the power I k dot x minus k prime dot x prime, and 2 I omega times minus I delta x minus x prime. So, here I will get a 2 omega, and using delta x minus x prime I can integrate out one of these variables. So, ultimately I get 2 omega integration d cube x e to the power I k dot x minus k prime dot x. Okay. Now, when I integrate this out, ultimately this becomes a 3-dimensional integration, and this will give you a 2 pi delta k minus k prime. So, after integrating you get 2 pi cube 2 omega delta k minus k prime. So, what we have seen is, if we evaluate this commutator here, we get 2 pi cube. This implies a k a dagger k prime commutator is equal to 2 pi cube 2 omega delta k minus k prime. You can do similar calculation to show that the commutator involving two A's or the commutator involving two A daggers actually vanish. Okay? So we now know what is the commutation relation between these A's and A daggers, which are nothing but the coefficients in the expansion for the field phi and pi, and these coefficients are operators because we are quantizing the system, and these operators obey these commutation relations. Now, what we will do is we will start with the expression for the Hamiltonian of the system, and we will express the Hamiltonian in terms of these operators A, k and A dagger k. So, let us do that now. So, the Hamiltonian is H equal to half Now, we have to substitute for the expression for pi of x and grade phi x and phi of x here. We have already worked out, we have already stated that phi of x is integration d cube k divided by 2 pi cube 2 omega times a k e to the power minus I k dot x plus a dagger k e to the power I k dot x. This is the only relation you have to keep in mind. From here we can derive what is pi of x. Pi is simply phi dot. So, when you take a time derivative, you will get d cube k over 2 pi cube 2 omega. Here all you will get is a minus I omega, because derivative with respect to time will give you minus I omega here plus I omega here, and as a result you get this is a k e to the power minus I k dot x minus a dagger k e to the power I k dot x. Similarly, what will you get for gradient of phi? Grade phi will give you a factor of I k d cube x over 2 pi cube 2 omega times I k, and the same thing here, a k e to the power minus I k dot x minus a dagger k e to the power I k dot x. So, we will now substitute all these expressions here and then do the integration, x integration as well as one of the k integrations, and then express the Hamiltonian in terms of the operators A's and A daggers. So, this is d cube k. So, the Hamiltonian now is H, which is integration d cube x, and you just see here you get pi of x square, right. So, there are two pi's, and for one pi I will use the integration variable as k, and for the other pi I will use the integration variable as k prime in order to keep them separate for one. Similarly, here you have grade phi square. So, for one of them I will use the integration variable as k, and for other grade phi I will use the integration variable as k prime. Similarly, for phi square also I will use k and k prime as the variables. So, I have three integrations, one over d cube x, and then I will get an integration over d cube k over 2 pi cube 2 omega, and also I have d cube k prime over 2 pi cube 2 omega prime. Then I have pi of x square, so that will give me minus I omega for one of the pi's and minus I omega prime for the other pi times a k e to the power minus I k dot x minus a dagger k e to the power I k dot x. That is for one of the pi's, and for the second pi I will get the same expression, except that instead of k I will have a k prime. So, a k prime e to the power minus I k prime dot x minus a dagger k prime e to the power I k prime dot x. So, this is the first term. The second term involves grade phi square. So, that is exactly similar to the first line, except that here I will get minus I plus I square times k dot k prime, and then again the same terms a k e to the power minus I k dot x minus a dagger k e to the power I k dot x times a k prime e to the power minus I k prime dot x minus a dagger k prime e to the power I k prime dot x. Then finally, I have the phi square, which will give me m square phi square term will simply give me m square a of k e to the power minus I k dot x plus a dagger k e to the power I k dot x times a k prime e to the power I minus I k prime dot x plus a dagger k prime e to the power I k prime dot x. We close the curly bracket. You can see that this term is identical to this term here. So, I can combine these two terms. However, the last term I cannot combine. So, let us rewrite this expression in a simpler way. This is d cube x d cube k over 2 pi cube 2 omega d cube k prime over 2 pi cube 2 omega prime times this will give me minus omega prime minus k dot k prime from these two terms, and then I have this expression a k e to the power minus I k dot x minus a dagger k e to the power I k dot x times a k prime e to the power minus I k prime dot x minus a dagger k prime e to the power I k prime dot x. And then the second term will be as usual. Let us put a bracket here, plus m square a k e to the power minus I k dot x plus a dagger k prime a dagger k e to the power I k dot x and a k prime e to the power minus I k prime dot x plus a dagger k prime e to the power I k prime dot x. All right. Now, there is a overall factor of half. Thank you. So, similarly here I will have a half. So, now I will multiply this term, I will open out and then I will simplify. Although this term looks little bit lengthy, when we multiply it and then carry out these integrations, we will get a simpler result. So, let us look at this term again. So, this forget about the a case for a moment. This will give you an integration of minus I k plus k prime dot x. Okay. On the other hand, if you multiply this term with this, it will give an integration over e to the power minus I k minus k prime dot x. So, you have integrations of this type. When you expand, you will get terms which involve, which have integration d cube x e to the power minus I k plus k prime dot x, and you will have integration d cube x e to the power minus I k minus k prime dot x. What will you get when you carry out this integration? In the first term, you will get the first integration will give you. Remember, here this dot product involves the 4-dimensional metric eta mu nu. So, you will get two terms here, d cube x e to the power minus I omega plus omega prime t times e to the power I k plus k prime dot x. Now, I can carry out this x integration here. When I carry out the x integration, this term will give me e to the power minus I omega plus omega prime t delta of k plus k prime. When I use this delta, this result will simply become e to the power minus 2I omega t delta k plus k prime. On the other hand, if there is a minus sign here, then you will get a minus here, and similarly there is a minus here. Therefore, when you multiply this with the delta function, the minus sign will cancel omega and omega prime. So, this integration here d cube x e to the power minus I k minus k prime dot x will simply give you delta of k minus k prime. Is this clear? There is a 2 pi cube, okay. So, there is a 2 pi cube yes.
Can you just explain again how omega plus omega prime became 2 omega?
This is you simply use delta of you know what is omega, right? Omega is simply square root of k square plus m square. Okay. Similarly, omega prime is square root of k prime square plus m square. Now you use the expression f of x delta x minus a is f of a delta x minus a. So, that will simply give, because there is a square involved here. So, k prime square you can simply replace it by k square, and that will give me 2. On the other hand, here because there is a minus sign, omega and omega prime will cancel and you will get simply 2 pi cube delta k minus k prime. So, we will use these two results in the integration to evaluate the Hamiltonian, and when I do that, what we will get is the following: h equal to half the x integration is carried out. So, all you will have is d cube k over 2 pi cube 2 omega times d cube k prime over 2 pi cube 2 omega prime minus omega omega prime minus k dot k prime. Let us now worry about the details of the operator ordering, because now A's and A daggers are operators, we have to worry about their orderings also, whereas e to the power I k x is a number. So, you do not worry about whether it is where it is placed inside the integration. Now, this multiplied by a k a dagger a k times a k prime, and the integration will give me e to the power 2 pi cube e to the power minus 2 I omega t delta of k plus k prime. So, this will have 4 terms. The first of the 4 terms is this, and then I will have minus a k a dagger k prime and the integration over x will give me 2 pi cube delta of k minus k prime. Then I will get minus a dagger k a k prime, again 2 pi cube delta of k minus k prime, and finally the last term minus a dagger k a dagger k prime e to the power 2 I omega t 2 pi cube delta of k plus k prime. This is the first term. This is plus, okay, thank you. Then I will have plus m square. Again this will have 4 terms, and these 4 terms are a k prime 2 pi cube e to the power minus 2 I omega t delta of k plus k prime. That is the first term. The second term is plus a k a dagger k prime plus a dagger k a k prime 2 pi cube delta of k minus k prime, and finally I have this term plus a dagger k prime e to the power 2 I omega t 2 pi cube delta of k plus k prime. Okay. So, now we have to combine all these terms. You can see this term here can combine with this term. Similarly, this term can combine, this term will combine, and this they will combine. What will you get when you combine? You see there is a minus omega. So, let us consider the first term here. In the first term, you have minus omega prime minus k dot k prime, and there is a plus m square here. All of these are multiplied by 2 pi cube e to the power minus 2 I omega t times delta k plus k prime, right. Now, you again use the fact that delta k plus k prime is multiplied to this whole term. So, for omega prime you write omega, but for k prime you write minus k because there is a plus sign here. Okay. So, when you do that, this term will become minus omega square plus k square plus m square multiplied by the whole thing 2 pi cube e to the power minus 2 I omega t delta of k plus k prime. What is this? This is 0 because omega square is k square plus m square. So, therefore, this term cancels. So, this term here cancels with this term. Similarly, the last term which involves 2 a daggers, you can convince yourself that cancels with the last term here, which also involves 2 a daggers. So, this cancels with this term. What remains is the terms which involve a's and a daggers, 1 a and 1 a dagger. You will see that this term does not cancel with this term, and similarly these two terms do not cancel each other. They add up, and the reason is that instead of delta k plus k prime, you have a delta k minus k prime, and therefore, there is a minus sign difference here, and because of which these terms do not cancel, and also there is a relative minus sign here. The signs work out in such a way that they add up. So, let us now write down what are the terms which survive. So, when we simplify, what we get is the Hamiltonian half integration d cube k over 2 pi cube 2 omega times d cube k prime over 2 pi cube 2 omega prime, then minus omega prime minus k dot k prime plus m square. Again, okay, let us write it in more detail. This times minus a k a dagger k prime 2 pi cube delta of k minus k prime minus a dagger k a k prime 2 pi cube delta of k minus k prime, and then plus m square, again the same set of terms, times a k, this time with a plus sign, a dagger k prime okay. So, I just rewritten all the terms which survive. Now, we can simplify these terms by carrying out the k prime integration. So, let us carry out the k prime integration. Then you can see that here you will get half integration d cube k over 2 pi cube 2 omega, and here I will get 1 over 2 pi cube. When I carry out the delta function, I will get again 2 omega for this. Here I will get minus omega square minus k square, and then there is a minus sign here that will make me omega square plus k square, and there is a m square here. So, this will give me plus m square times 2 pi cube, and then a k, a dagger k, a k, a dagger k. When you evaluate the second term, again you will get the same thing here, in the sense that there is minus, that minus multiplying with these two minus will give me plus signs, and this m square will add. So, you will again get omega square plus k square plus m square times 2 pi cube, but instead of a k a dagger k, you will get a dagger k a k. So, you have all these terms here times this plus a dagger k a k. Okay. So, the complicated looking Hamiltonian now takes a very simple form. You will again, you can use the relation that omega square is equal to k square plus m square. So, this will give you 2 omega square. This 2 pi cube will cancel this 2 pi cube, this 2 omega here and there is a 2 omega square here, that will cancel to give me simply omega. So, when I simplify, what I will get is that the Hamiltonian of the system is half integration d cube k over 2 pi cube 2 omega times omega times a k a dagger k plus a dagger k a k. Okay. So, this is the Hamiltonian that we got at the end. Now, our task is to find the spectrum of this Hamiltonian. So, what we will do is that we will start with this Hamiltonian in the next lecture, and then we will derive its spectrum, and then we will discuss some of the difficulties associated with this, and then how to interpret them and so on. Okay. Yeah, so this is for convenience. You can cancel this omega here, but I want to write it like this because this term here, the whole combination here is Lorentz invariant. So, in order to have manifest Lorentz invariance, I just want to keep the integration measure always as d cube k times 2 pi cube 2 omega. Okay. Any other question? Okay, then we will stop here today.